called vector functions. Vector functions become really important as you go on if you want to model anything moving in 3 dimensions, something moving in space. So I'm going to start by reviewing something from Math 5B and Pre-Calculus, which is parametric equations in R2. Now, if you feel like you need a little review on that, section 10.1, very important that you're familiar with parametric equations. There is a video, I have a video in the module that goes through that if you need to review that. I'm going to do a quick example, but if this doesn't sound familiar to you, you need to go back and review. All right, so if I have a pair of parametric equations like this, it's telling me what x does as a function of t and y does as a function in t separately, and it implies that x and y are related to each other. And so we often want to know, okay, well, how are x and y related to each other? We want to take a look at y in terms of x. And the way that we learned how to do that, one of the ways, is to eliminate the parameter. And in eliminating the parameter, there's lots of different ways. It depends on what our equations look like, so you might want to go back and review that. In one like this that has a sine and a cosine, typically what we're going to do is to isolate the sine and the cosine. So that first equation could be x over 2 equals sine of t, and y equals cosine of t. When we isolate those, then often what we'll see is that if we square both sides of both equations and then add them together, we'll get x squared over 4 plus y squared on the left, sine squared of t plus cosine squared of t on the right. So I'm just adding together. And sine squared plus cosine squared, of course, is 1. So I get x squared over 4 plus y squared equals 1. And so we see a familiar equation here. This is the graph of an ellipse. 2 units in the x direction, 1 in the y. And so we get this ellipse. Now, when we eliminate the parameter with parametric equations, the only problem with that is once we've done that, we lose information. In this case, we lose the dependence on t. For instance, if I were to substitute t equals 0 into these equations, sine of 0 is 0, cosine of 0 is 1, I would get x equals 0, y equals 1. So that means I'm at this point, 0, 1, at t equals 0. So if we're thinking of t as time, we're at that position when t equals 0. We can do this for other points as well. Suppose I put in t equals, say, pi over 2, just because it's easy to substitute in. Sine of pi over 2 is 1, cosine is 0, so I get 2 comma 0. So I'm here at this point when t equals pi over 2. And if we put more and more points in, we can see that what's happening is this is modeling movement along this curve. The black curve itself is the path that we're on, but we're modeling movement around this ellipse in this direction. So those yellow arrows are the direction of movement, the direction of increasing t. So sometimes when we eliminate the parameter to get the graph, we then have to go back and see if we've lost any information. For instance, we might lose information about the direction of increasing t, but sometimes we also can lose domain information. So again, if you need to review that, you should go back and do that. One other thing that we learned back in 10.1 is that if we can't eliminate the parameter, what we can sometimes do is to look at x as a function of t and y as a function of t separately. So what I mean by that is this equation here, x equals 2 sine t, if I were to draw that on axes, and I have this one on the right and the other one on the left, so it could be confusing here. So x of t is this one. X of t is 2 sine t. So we go 0 up to 2. 0, -2, 0. So that's telling me what x is doing as a function of time. X is going from 0 to 2 to 0 to -2. What does that tell me about what's happening on this graph? X over here is horizontal motion. So X starts at 0, it gets bigger and then smaller. So what that means is if I just look at the horizontal motion here, X starts at 0, it gets bigger until we get to X equals 2, and then it gets smaller till we get to X equals 0, and then X equals -2, 0, and so on. This tells me about the horizontal motion. 0, 2, 0, -2. Horizontal motion. 0, 2, 0, -2, and so on. This one is y as a function of t. So y is cosine t. This is the graph of cosine of t. It starts out at 1, and it goes from 1 down to 0 to -1. Y is telling me about the vertical motion over here. So at t equals 0, y equals 1, and then it goes down to 0 to -1, back up, and so on. So this by itself is telling me about the vertical motion, and this one's telling me about the horizontal motion. And if I put these two ideas together, I can get a feel for this. What I mean, for instance, is if I put in t equals 0 on this graph here, I get x equals 0. Putting in t equals 0 here, I get y equals 1. So at t equals 0, I get the point x equals 0, y equals 1, which we had already drawn there. And then what happens from that point? From that point, as t increases from 0, x is going to increase. That means from this point, x is going to increase, which means we're going to go to the right. What is y going to do? As t increases from 0, y is going from 1 down to 0. So y, as t increases, we have x moving to the right and y moving down to the right and down. Let me actually put that in here. X is moving to the right, that's what that blue graph is telling me, and y is moving down. Putting those together, we're moving to the right and down. This is our direction. So sometimes when we can't eliminate the parameter and we want to try to get an idea of what's going on in the XY graph, we can graph these individually, and that tells me how X acts as a function of time, which tells me horizontal movement, and how Y acts as a function of time, which tells us vertical movement. This technique, we learned it back in 10.1. We maybe didn't use it quite as much, but we're going to need it here when we move into 3 dimensions. All right, so this is old news. What does this have to do with a vector function? If we take these two equations and we write them as a vector, that's how we're going to define what's called a vector function. So we're going to treat this like this is a function where we put in a value, but what we get out is a vector. So that's new. We haven't done that before. But for instance, if I put in r of 0, so if I put in 0 for t, I get 2 sine of 0, so 0. Cosine of 0 is 1. I get 0, 1, but I get the vector 0, 1. Not a point, I get a vector. So where is that vector in my picture up here? Well, it's a vector that is pointing from the origin to that point 0, 1. It's pointing to where that object is on that curve at that time. And as t increases, what that r of t is going to do is it's going to point to where we are on the curve at any given time. Now those vectors that are generated here, that's not what we're going to call the graph of the vector function. Graphing all those vectors is not what's going to be called the graph. What is going to be called the graph is that if we picture on the tip of that, those vectors, some paint, the graph of the vector function would be that path that is traced out along there. And so graphing the vector function is similar to, or it's the same thing as, actually graphing that pair of parametric equations. It's just looking at it in a new light. So we think of the graph as being traced out by the tip of R of t. So we've defined what a vector function is. This is a vector function in 2 dimensions. We'll look at vector functions in 3 dimensions in just a minute. And we've talked about what the graph of a vector function is. We're also going to talk about things like domain and range and limits and derivatives and so on with this new kind of function. All right, so when we move into R3, we have x and y and z all separately as a function of t. And if we want to know what this generates when we're in R3, here's the idea. For any given value of t, you'll get a 3-dimensional vector. That's this blue part right here. And as t changes, that vector changes. So just like the gray vector we had in the last problem, at t equals, say, 0, it might be here. And then t equals 1, it might be here. And t equals 2, it might be here. And so the curve that we would get, if we put a little black ink on the end of that, that curve that we get, that would be the vector function r of t. It's going to be a curve in 3 dimensions. And so using vector functions is the only way that we're going to be able to talk about curves in 3 dimensions. So if we want to talk about motion of an object in 3 dimensions, this is how we're going to do it. To sketch these curves in 3 dimensions, which are called space curves, what we're going to do is similar to what we did in 2 dimensions. Anytime I have a vector function like this, I can also write this parametrically. So x is cosine, y is sine, and z is t. And we're going to do something similar to what we did in 2 dimensions where we eliminate the parameter, but oftentimes it's going to be hard to try to eliminate the parameter of all 3 of them at the same time. So typically what we're going to do is we're going to take a pair of those equations and we're going to eliminate the parameter with that pair. Now, which pair? How do we know? We're going to do lots of examples, you'll see. But in this case, I'm going to take that pair because from my 5D experience, I'm familiar with that. That will be x squared plus y squared equals 1. Square each of those, add them together, I get 1. Now in 2 dimensions, in the xy plane, that would be the circle of radius 1. And the direction of increasing t, when t equals 0, I'd be at the point 1, 0. This corresponds to t equals 0. So we're going around this curve, but which way do we go? Do we go this way or do we go that way? Well, in this case, I know I'm either going up and to the left or down and to the left from that point. And so either way, I'm going to the left. What I want to know is from t equals 0, am I going up or am I going down? So I want to know what y is doing as t increases from 0. That's how we figure out the direction of increasing t. So what is y doing? As t increases from t equals 0. So if I think about what y does, now you don't have to graph this, but this is what I'm thinking of in my head. If I think of y as a function of t, y is sine of t. So as t increases from 0, what y is doing is y is getting bigger. It's going from 0 to 1. As t increases from t equals 0, y gets bigger, y increases. So that means from this point here where t equals 0, we're going to start by moving upward. Y is going to increase. And so that tells me my direction of travel is this way, counterclockwise. A lot of times people are a little rusty on that idea. How do we know the direction of increasing t? If so, go back again, once again, and review 10.1. All right, that's 2 dimensions, but we're in 3 dimensions. So how does this translate to 3 dimensions? Well, in 3 dimensions, this graph right here is not just a circle, it's a surface, right? X squared plus y squared equals 1 is the cylinder of radius 1. So let me mark this as a 1 here. I missed over here. Let's just radius 1 there. Okay, so the cylinder of radius 1. Now that doesn't mean that's what this function is. Remember, this function is just a curve in space. What this is telling me is that this surface is a surface on which my curve lies. My curve is being drawn somewhere on this surface. If you thought of this as like a roll of paper towels, that's what I'm going to draw on. I don't know what it looks like, but my curve is going to rest on this surface. So when you eliminate the parameter, what you will get is a surface that the curve is on. I also know from this about the XY behavior. So if I look at the red part, that tells me about the XY behavior. It doesn't tell me anything about Z, but it tells me what X and Y are doing relative to each other. So specifically, if we looked at t equals 0, we said we were at the point 1, 0. Now if I put t equals 0 here, I also get z equals 0. So at t equals 0, I would actually be at this point on my surface right there. That black dot is for t equals 0. And what I know just about the xy behavior, so I'm not bringing z into this yet, just the xy behavior. It goes from the positive x-axis to the positive y-axis and around. What that means to me in this picture is we're going to be going around this cylinder like this, and around and around and around. Now, I don't know vertically what's going on. I don't know as I go around, am I going up and down? Am I going to infinity? I don't know the vertical motion, but I do know that the XY motion, the XY behavior, is that we're going to be going around. Here, let me put it up here. I'm going around the front and around the back. I'll make it dotted where I'm talking about behind. Okay, so I'm going around the front, then the back, around the front, and then through the back. And as I said, I don't know about the vertical motion as I do it. It could be going up and down like I'm going around a merry-go-round, but I do know I'm going around. Once I've established what X and Y are doing, then I want to bring Z into the picture. Z is T. So you don't have to graph it, but Z as a function of T just looks like this. As T increases, Z increases. So as T increases, Z increases. Which what that means in 3 dimensions is that the point is going upward. So I previously said we're going around the front and then we're going to the back, going around the front, going to the back, but I didn't know what Z was doing. Now I do. As we go around, the whole time, Z is getting bigger. I'm going to erase this here in just a second, but I'm going to go around and get bigger, go around and get bigger. So the whole time I'm going around, Z is increasing. So to get a little bit better idea, when is it going to come back around? Where does it come around? Is it going to come around really close here? Is it going to be a spring that's all stretched out? Well, to make one revolution, we know in 2 dimensions here, one revolution would be when t equals 2 pi. So if I put 2 pi into my vector function, or into my parametric equations, cosine of 2 pi is 1, sine is 0. That's what we said, we're going to come back around. And t is 2 pi, so this is going to be 1, 0, 2 pi. So 2 pi is around 6.28. So that means by the time I come around again, z is going to be around 6. So let me make these units of 2. So just bigger than 6 like this, that's where we're going to make one revolution. So we're going to go around. We're going to go around. Then we're going to go behind. And then we're going to come like this. So we're going to go around. And we're going to go behind. And we're going to come up. And it didn't start at t equals 0. So even before this happened, down here at negative 2 pi, so around negative 6, we go around the front. We go around the back, come around the front. This is going to be our direction of travel. This is the direction of increasing t. We established that here. This is one of our most basic curves. This is called a helix. And helices, that's the plural, helices are really important, for instance, in the study of genetics, because DNA is actually a double helix. So I took a class one time at UCLA in graduate school all about the math of the DNA. It was really pretty interesting, and it was all using vector functions. All right, so what do? We take a pair, we eliminate the parameter, that gives us a surface the curve is on. We draw that surface to give us a little bit of a depth perception here. We figure out how those two variables relate relative to each other. Then we bring in the behavior of the third variable. Now, just to make sure you've got the idea of that, bringing in the behavior of the third variable, here is the same, well, not the same vector function. These two parts are the same, but this is new. So these two parts are the same as they were in the last example, which means we're still on that same cylinder. X squared plus y squared equals 1. Okay, we're on that cylinder. But this time, how does z behave? Well, z is a function of t. Z equals e to the t. So, for instance, at t equals 0, just to give us a kind of a starting point, at t equals 0, I would be at 1, 0, e to the 0, so 1, 0, 1. So at t equals 0, x is 1, these are 1s here. Y is 0, z equals 1, so we'd be up here. Let me make this 1 here. So like this. And we've already said from the last problem, we know the behavior of x and y is coming around the front and then going around the back that way. So if we're looking down from the top, it would be counterclockwise. So as we go around, just like before, z is increasing as t increases, but it increases much more quickly. So it's not like last time where, we're going to go around and by the time we get to 2 pi, we'll be back here. Oops. we're going to be much more spread out again. By the time we get around, if I wanted to put in 2 pi, putting in 2 pi, still I get 1, 0 again, but now I get e to the 2 pi. And that's a really big number. So that means as I go around, and I go around back like that, it's, you know, it's off the charts. This is 1, 0, e to the 2 pi. So it's very stretched out. In fact, if you graph it on the computer, you would have to shrink your scale down really, really small to even see it come around again. But it does continue to go around. Now, what happens over here, though? What happens when t goes to negative infinity? We know at t equals 0, we're here. But as t goes to negative infinity, we're still going around and around and around. I'm going backwards now, so around the front, around the front, around the front. But z approaches 0. It never equals 0. It just approaches 0. So what's happening, it's not going to show it very nicely in my graph, but what's happening as it goes around is it's going to be coming towards that xy plane and being very tightly spiraled, but never touching the xy plane. Z is always 0. Now I drew it going backwards, but it really is going this way. We're going around this way. We're going around this way. So it's like a spring that we squish down real tight to the xy plane and then stretch this part out. Okay, so that's just to kind of show you, you get the idea of what's going on with x and y, and then you look at the behavior of z. Here's a similar problem. This actually is also a helix. We're going to look at a lot of examples that are more interesting than a helix, but just to get our basics down. If we were to take x squared plus y squared here, we would get sine squared plus cosine squared, which is again 1. But if you'll notice, oops, from the last 2 examples I did cosine sine, this says sine cosine. So this is still the path in 2 dimensions, but what changed is the direction of t. If I put in t equals 0 here, I get 0 and 1. So at t equals 0, we're here. And the question that I want to answer is, are we going to the right and down from here, or are we going to the left and down? So I want to know, am I going around to the right or am I going around to the left? As t increases from 0, are we going right or left? And so in order to figure that out, this time I'm going to look at x. Last time I looked at y, but that's because I was here at t equals 0. So I wanted to know if I started by going up or down. Now we're here. I want to know, do we start off by going right or left? So I'm looking at what x does. X here, x is sine of t. So sine of t looks like this, which means that as t increases, x is increasing. As t increases from 0, x increases. Which means on my green graph there, I'm going to start by moving to the right. And so that means our direction of increasing t here is this way, this time. So it's clockwise this time. X squared plus y squared equals 1 is our surface on which our curve lies. So just as before. But this time we're going from the positive y-axis to the positive x-axis. So picture when t equals 0, when t equals 0, I'd be at 0, 1, 0. So when t equals 0, we're here. Okay, 0, 1, 0. But we're going from the positive y-axis around towards the positive x-axis. That means we're doing our motion where we're coming around the front towards the back, around the front towards the back. Okay, so if you're looking down, this time it's clockwise if you're looking down from the top. So from here, we're going around the front, then back, around the front, and then back. Z is t. So one revolution would be t when t is 2 pi. So the z value would be 2 pi. So this is like the two examples ago where one revolution is going to be 2 pi. So this would be 1, 0, 2 pi. And we went around this way this time. All right. Couple things that I really want to see to get full points on these graphs here. When you're graphing these space curves, there's a couple things you need to see, because if I were to have drawn this graph and you didn't see me drawing it, for instance, let me just, don't look for a second. Now look, here's my curve in 3 dimensions. You have no idea of depth perception here or direction of increasing t. It's not clear to me if this part is closer to you and this is behind, or this is behind. You can sit here and do an optical illusion about what's actually going on here. So the way that we help with that optical illusion is we make sure we show 3 things here. One is you need to show a surface that the curve is on. A surface that the curve is on. Okay, in my case, in all 3 of my examples, it was that cylinder. Now, if you're not using color, you want to make sure that that surface is lighter, like maybe a really light color pencil where the curve is darker, because you want to make sure you realize that the surface itself is not the graph. It's helping me visualize the graph, but it's not the graph. So a surface that the curve is on, you need to show that. You need to clearly show the direction of travel, so the direction of increasing t. Okay, the reason I say clearly is sometimes I see little arrows here and it's not very clear. In fact, one could argue here that I probably should have shown a little more here. I might want to go back and erase this red part here, was just where I was trying to show you how x and y behave, but that's not part of my final graph. Right, so it needs to be really clear. And then the other thing to help us from seeing an optical illusion is we should have a dashed, dashes or dashed curve when behind the surface. Okay, that's what I did here. If you'll notice, when I was around behind, I made it dashed so it's lighter. And the reason why I do that, once again, and I didn't do it very well here, but I did it here as well. I did it right here. But if you don't put that in, it is really easy to look at this and think, oh, this is going around the back, and now this is the front. This is the back, and now this is the front. It's very easy to see it in the wrong way. Okay, so these are the three things I want to see when you do these graphs. The next couple of videos will have some more examples where the surfaces are not just the cylinder every time. So take a look at those.